Viewer discretion is advised for this video. This story may be too scary for some viewers. We, the makers of this video, in no way support or condone the actions of the subjects featured. How did quantum entanglement terrify scientists? Albert Einstein referred to quantum entanglement as spooky action at a distance. But how did this phenomenon come to be, and what was so terrifying about it? Keep watching to find out. You won't want to miss this. It all started with a question. Can we trust our scientific methods? It sounds simple enough, but it led to one of the most unbelievable discoveries in history. At first glance, it might seem like we do live in a predictable world. Cause and effect, Newton's laws of motion and gravity. Things happen for reasons. If you hit a ball with a bat, it flies away from you. If you drop a glass, it will fall to the ground. The moon will orbit the Earth, and eventually the Earth will orbit the sun. These are just some examples of the cause and effect relationship that governs our daily lives. Or is it? In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper that changed everything. They thought they had discovered a fatal flaw in the foundations of quantum mechanics. They argued that the established rules governing the behavior of subatomic particles were incomplete and did not accurately describe the nature of reality. According to them, there was more going on beneath the surface. In their view, the universe didn't operate according to the principles of quantum mechanics. They called these principles the statistical or probabilistic interpretation of quantum mechanics. They theorized that quantum mechanics was only a partial theory and that it should be replaced by a more comprehensive explanation of reality. They dubbed this new theory a theory of local realism. However, their peers largely dismissed their work as an overly complicated attempt to disprove quantum mechanics. But Einstein was undeterred. He continued to express his doubts about quantum mechanics until his death. He even called quantum entanglement spooky action at a distance. What exactly was he talking about? To answer that question, we must turn to another revolutionary scientist, one whose name is synonymous with the study of quantum mechanics, Richard Feynman. According to Feynman, everything in the universe is made up of tiny vibrating filaments. We call these filaments strings because they look like guitar strings. When these strings vibrate, they create sound waves. These sound waves travel through space and can interact with each other. When two sound waves meet, they either cancel each other out or add up to make a bigger wave. Feynman realized that the same thing happens to matter. However, instead of sound waves, quantum mechanics governs the interactions between vibrating strings. One of the phenomena predicted by quantum mechanics is quantum entanglement. Quantum entanglement occurs when two or more subatomic particles become linked together in such a way that they share the same fate regardless of the distance that separates them. Imagine you have two coins and you flip them both. If you get heads on one coin, you know that tails must have turned up on the other. If you flip the coins again, you would expect the same result. This is because the laws of classical physics govern the behavior of everyday objects. However, in the quantum realm, things are very different. Quantum entanglement is a lot like the interaction between those two coins. When you flip one entangled particle, you know instantly what state the other particle will be in. The only difference is that it's not always the opposite. For example, if the first particle is spinning clockwise, the second could be spinning counterclockwise or vice versa. But here's where things start to get weird. Suppose you don't actually observe the first particle spinning. In that case, it exists in a state of both clockwise and counterclockwise motion until you look at it. Once you do, the wave function collapses, and the particle is observed to be spinning in only one direction. Now, here's the kicker. If you were to measure the second particle at this point, it would also be found to be spinning in the opposite direction. So even though the two particles are separated, they still influence each other's behavior. That is quantum entanglement. Einstein and his colleagues weren't convinced. They believed that this was just a statistical relationship and that there was more to the story. To understand their argument, let's consider a simple example. Imagine you have a box with 2 kittens in it. You know that at least one of the kittens is black since you saw one when you opened the box. However, you don't know which one is black and which one is white. In this scenario, the cats represent quantum entangled particles, while the knowledge that at least one is black represents the wave function. In other words, the wave function tells you the probabilities of finding a particle in a particular state. Before you open the box, both cats exist in a superposition of being black and white. Opening the box is analogous to making a measurement. When you observe one cat, you collapse the wave function and determine the state of both. This illustrates the essence of Einstein's argument. He believed that this apparent connection between entangled particles was nothing more than a statistical correlation caused by hidden variables, not a real physical connection. This is why he referred to quantum entanglement as spooky action at a distance. After hearing that, you may be wondering why anyone would think that quantum entanglement is anything other than a statistical relationship. After all, if you know the outcome of one entangled particle, you know the outcome of the other. So what's so mysterious about that? Well, as strange as it may sound, quantum entanglement has been experimentally confirmed many times over. We now know that 2 entangled particles remain connected no matter how far apart they are. Even if they are light years away from each other, the moment you change the state of one, the other changes instantaneously. That means something is happening faster than the speed of light, which is impossible according to Einstein's theory of special relativity. This brings us back to the original question: can we trust our scientific methods? If quantum entanglement is real, then it means that Einstein's theories about the universe need to be revised. Einstein was reluctant to abandon his ideas, but the evidence for quantum mechanics was overwhelming. He once said, "If I had to start over again, I would not bother about the other." That was a reference to his earlier work on special relativity, which was based on the idea of a hypothetical substance called the luminiferous ether. As it turns out, the ether turned out to be unnecessary. In order to explain the behavior of light, this suggests that there may be other areas of physics where our current understanding is incomplete. In fact, physicists have conducted experiments that show that quantum entanglement is real. In one experiment, researchers at the University of Vienna created a pair of entangled photons. They then sent each photon in a different direction and measured their polarization. Polarization is a property of light waves that describes the orientation of the wave relative to the direction of travel. Photons can be polarized in any direction, but only two states can exist at the same time. Researchers found that if they changed the polarization of one photon, the other photon's polarization changed instantaneously, regardless of the distance between them. Other experiments have confirmed these results and shown that the effects of quantum entanglement are not limited to photons. Entanglement has been observed in other types of particles as well, including electrons, protons, and atoms. In recent years, scientists have begun to harness the power of quantum entanglement for practical applications. One promising area is quantum computing, where entanglement can be used to create extremely powerful computers. Another area is quantum cryptography, where entanglement can be used to create unbreakable encryption codes. So what does this all mean? Einstein was right that quantum entanglement is spooky action at a distance, but he was wrong to think that it could be explained by hidden variables. The connection between entangled particles is real and it is instantaneous. This means that our understanding of the universe is incomplete and that we need to revise our current theories. The implications of this are far-reaching. It suggests that there may be other areas of science where our current understanding is also incomplete. We may need to re-examine our assumptions and look for new explanations for various phenomena. The study of quantum entanglement is just beginning, and we have only scratched the surface of its potential applications. As we learn more about this amazing phenomenon, we will undoubtedly find new ways to use it to our advantage. We hope you enjoyed this video. Please like, share and subscribe to eTryS1010, YouTube's fastest growing channel of the history's most shocking facts. Thanks for watching. We'll see you next time.